and I want him to define to me what a function is.
Where you put an input and get a separate output?
That's not bad, that's not bad. The problem is, if I was to write down this is P equals mq plus c, that's like y equals mx plus c for this curve. If I say that P is a function of Q, this is maths notation, function of Q, then what I'm saying, like Matt said, is you input values of quantity and you get price. I'll talk about that in a minute. But let's say it's that. And what that means is that if I say that, then it means it holds for every single value of x and y, or in this case quantity and price. So really I should be drawing this and going on forever. And the problem we have is this doesn't exist, and neither does this. You can't really have a negative quantity, and you can't really, it doesn't make sense to have a negative price for a good. So what we need to do, when we draw it, we scrub off these axes. And if we want to be precise and consider maths correctly, when we're defining this as a function, to make it a function, we have to say that P and Q are greater than or equal to 0. Else, it isn't a function, and we are being imprecise in our use of maths already. So if I don't write this in the future in this lecture, then it's because I'm being bad at maths. And it's because I've forgotten, it doesn't really matter. But if I don't, you can remind me if you're pedantic. But really, I should be writing that. So that's non-negativity. And the final one is axes. Now, I just want you to think back to GCSE science. And when we look at a graph, and hopefully Matt can answer this. So we have what's called the independent variable, not you, Matt, the other Matt. I'm picking on you today. I'll class Tim in a minute. Well, we have what's called the independent variable, which is the thing that we choose to change, and the thing that can change. So when we look in science, we might change the temperature for an experiment. And then we have the dependent variable, which is the thing that changes as a result of what we're changing, and we measure the change. Now, that should be familiar. Is it familiar? You should be fairly familiar. You know what I'm about. So if we think about economics, and you know that the independent variable should go on the x-axis, that's what the scientific convention is. And on the y-axis we put the dependent variable. Now think about this though. What changes? Price. So we've got a problem here already. We're not doing what maths does. We're not putting the independent axis on here, and we're not putting the dependent one on here. We're doing it the other way. I wish Marshall was alive. It was Marshall who came up with this code, so I'd ask him why he did it. Because all it does is it creates a tremendous amount of problems for us when we're trying to deal with mathematical uses in economics, such as supply and demand. Well, really, it doesn't create that many problems, but for those of you who know the term, all we have to do is take the inverse function of price and the equation we have. Every time we look at supply and demand, we need to take the inverse function. And you won't notice if I do that today, but we have to, which is an absolute pain. I mean, if Marshall had just done it the other way around, it would have helped us a lot. I need a drink. Yeah, so I'm just going to try and quickly derive this result I put on the board. You can have a look at it and see if any of it means anything here. That should make sense already, as we talked a bit about that. I need to scrub my board, because... can you all see that? Is that big enough? Yeah. Do you want me to do bigger? I wish I had blackboards, because I could clean it up. I feel like Mr. Kanye right now. So if we just draw a graph of demand, price and quantities, and we set it down slowly, then if we're looking at the equation of this line, we normally write that y equals mx plus c, or in our case, the problem I'm going to get here is I would say that price should be y, price should be x. So that's, you know what I was saying about the axis being along around it becomes a big mess. So instead of using this, y equals mx plus c, I'm going to use a much better method of defining a straight line, which the year 11s might not know, but essentially it's exactly the same thing, and that's that ax plus by equals c, or in our case, it doesn't matter which way I get these around now, ap plus bq equals c. Now if I do a bit of jiggery pokery, what do I want to get? I want to get, so I want to get bq equals c minus ap. I've taken the ap and put it on this side. And now what I'm going to do is I'm going to quickly divide by b, so we get that q equals c over b minus a over bp. Now what we need to remember quickly is that c over b and a over b are just numbers, because the a and the b, like the m and the c, are just numbers, they're not changing. The things we change are y and x, or P and Q. So really, we can just say, if we let C over B equal D, and likewise let that over E, we arrive at Q equals, I'll keep it capitals, it doesn't really matter, Q equals D minus E lots of P, and then of course I need to write that Q and P are greater than or equal to 0, and the final thing I've to note is that what that means in words is D and E are elements of the real number set, which just means basically that D and E are numbers. So that is a good mathematical definition of the demand curve. It's quite precise, it's good. Now you should all know about movements and shifts in demand, which I'm quickly going to go over mathematically. A movement is quite simple. A movement really isn't a movement, it's just where we go from one point to another. So I'm going to write up here, because this is, for some reason, the equation I always use, which is that Q equals 27 minus 3P. It gives us some quite nice numbers. That's the example I'm going to make. So say we've got a point here, and we've got a point here. I have to get my numbers right here. I have them written down. This might come out wrong. I need to think of some good numbers. Anyone think of a good number? Choose 1 and 2. This isn't going to be very accurate then. I'll say P is 2 and 1. So if we can find the ones representing this with a simple bit of algebra, so if P equals 2, Q is going to be 27 minus 3 times 2, which is 21. And if P equals 1, then Q is going to be 27 minus 3, 24. Am I right? Yeah, I have. And so a movement is simply just another point on the curve. And as we see, it can only be caused by a change in price, because Q, the only thing Q is dependent upon, because 27 and 3 aren't going to change, is P. So that's why a movement comes only in a change in price, because the only way we can move to another point is if P changes. So that's the only way that the movement works. And now if you remember your economics you're taught in this classroom when you're doing GCSE, so that a movement is caused by a change in price. Well, I hope that makes sense now mathematically. The second one is a shift. Now a shift is when for a given price, so let's take this as our given price here, for a given price, the price isn't changing, the quantity at every price increases. So we've moved from here to here, I don't know what this point is. But if we look at here, what we've said is that we have a given price, and a given price means that price isn't going to change. So we've got a thing that isn't going to change, a thing that isn't going to change, and a thing that isn't going to change. But Q changes, so we get an increase in Q. And the only way we can do that is if we add on a quantity. So that's how we represent. Now this C, as you see here, doesn't really matter, is polar. Classic Carney acronym there. So that C is what causes this shift. So we have to add a bit on. Now, if this is in GCSE maths, it's quite advanced, but if we say that Q equals a function of P, then if I say that Q now becomes a function of P plus C, what should the graph do? Shift which way? Up? Vertically, right. But what it doesn't, shifts this way. And that's because, again, the axes are the wrong way around. So again, it's creating us more problems. So that doesn't really hold with maths, even though that's what we're doing. It makes sense. Price is staying the same, but quantity increases, so we need to add on something, and yet it's moving this way. You could say likewise it was moving up, but that's not how we define a shift. A shift is for a given price changing the amount of quantity. It's not for a given quantity changing the amount of price. So that is demand done. I'm going to say nothing about supply, because supply is boring, well not boring, but it's exactly the same. Supply is just like with linear upward sloping, except the law of supply states that for a given ceteris paribus for a normal good, an increase in price will lead to an extension in supply, not a contraction in demand. So I'm not going to dwell on that. And the final thing I'm going to do on demand, checking what the time is, I'm doing alright, is look at equilibrium positions. So how can we find the equilibrium quantity and price? I'll keep exactly. When we know the linear demand curve and the linear supply curve. So I'm going to introduce two examples. QD equals 27 minus 3p, and QS equals 15 plus 3p. And what you should notice there, and it will scream out to you by the time you've done enough of maths, is that we have two equations here and two unknowns. And when we have two equations and two unknowns, we know how to find the values. We just have to solve them simultaneously. So when we're finding this equilibrium position, when you draw your demand and supply curves, so I've done it. Oh, I did it wrong here. See, I'm not very good. I'm not precise enough as a mathematician yet. Hopefully I'll get better when I go to uni. We're looking to find this point. And I'm going to call it Q star and P star. I like the star, I don't know why. That's supply, that's demand. And we want to find this mathematically, and we have a good technique to doing this. Now, Q star, well, I'm just going to read my PowerPoint now, is it? Q star is the point where QD equals QS. So, many people might look at this and say, we've got quantity demanded, we've got price, and we've got quantity supplied. So really, we've got two equations, 1 and 2, and 3 unknowns. But we don't, because we're finding the point where QD equals QS. So if QD equals QS, we can just change this to a D, or we could change that to an S. So now we do have two unknowns and two equations and two unknowns. So there's three methods up there to solve these, to find P and Q, P star, Q star, such that for these two equations. And the most obvious one is to add together. So if we add these two equations together on the left-hand side, we get 2QD, that's a falling space, 2QD equals, now this number's 42 I think, yeah. And if we have minus 3p plus 3p, it goes to nothing, so they just cancel out. So 2QD equals 42, QD equals 21. So we found QD, and now all we have to do to find P is just rebang it back in here. So you'd have 21 equals 27 minus 3p, and take that over there, so you get 3p, minus 21 from both sides equals 6, p equals 2. So we found this point is 2, and we found this point is 21. And the other method, we've got a subtraction. If you wanted to subtract these two equations, you'd still come out with P and Q, and you could substitute as well. You could make this part of the equation be here, because QD is defined as this, and this side is QD. So we can just bung this here, and we can find P and find Q. And the substitution is the most important method of solving. Addition is the easiest here by far. We can just add them together and P and Q. But substitution is the most important, because when we have curves that aren't linear, and we can't just add them together, it will get easier. So substitution is probably the best method to solve. And that's application 1 done. So I won't be using the whiteboard for a teeny bit. This is quite short actually. I wanted some breaks for those who don't like maths. It won't be very good. I've done a bit here. I could have done more. I mean, if someone wants to do a lecture on the philosophy and the history of maths for economics, then they could fill one that evening. I don't think Joe will be very interested in that. But there's a lot to talk about that, and there's a lot to talk about why we use maths, how we use maths, when we use maths. But I just wanted to do some maths really for my first one. But I thought I'd give you a bit of a break. Now, Jevons, I'm looking really here about when maths started to be used in economics, and it was fairly early. So we got this Victorian English economist, great man Jevons, he was called the founder of mathematical economics. He wasn't the first man to use maths in economics, but he's called the founder. And Jevons said this quote, and that economics must be mathematical because it deals with quantity, which is a bit like what I said earlier. Most of the concepts in it are numbers, so we should use numbers in it, and it makes sense to me, and it makes sense to Jevons, obviously. And those of you who apply to UCL for economics will probably go to the Jevons lecture room, and because he was based in London and UCL, and they've named the whole lecture room around him. And he was also the first guy to. The maths he started with was called marginal analysis, and marginal analysis is when you look at really, really small changes. And for those of you who are good enough with calculus knowledge, really, really infinitesimally small changes are derivatives. So when we're looking at marginals, he was looking at derivatives and differentiation, and he applied that to economics in all the marginal cases. So when things change by a teeny amount, you can start looking at the derivatives on them. Now the second two are, I don't know how to pronounce his name, so I'm not good at French, but I know the second one is Valraz, because I'm doing my EPQ a bit on him. And these two were French, and they, if you look at the dates, they were before Jevons, so really you could say they started it. But Jevons is said